Alrighty. So if we drop a rock near the surface of the Earth, its velocity increases by 32 feet per second for each second the rock falls. Is the velocity of the rock a linear function of the time since it was dropped? So what I'm going to do is drop a rock near the surface of the Earth. So in other words, let's say you're up on top of a building. Let's say you're up on top of, and you should never do this, but let's say you are up on top of a building and you drop a rock. Here's the rock, and the rock falls down and hits the surface of the Earth below, right? Basically, it gets faster and faster as it falls, right? It gets faster and faster as it falls. Now, of course, there's air resistance that helps it to finally, the air resistance that pushes back against it eventually causes the rock to go at a constant velocity. But initially, anyway, the air resistance is minimal and the rock certainly speeds up faster and faster as it falls. That's all we're trying to say. So we're going to do a little table just for fun, and I'm making this up, okay? So I'm going to do like time in seconds, right? And I'm going to do the, let's see, the velocity in, it's feet per second, all right? So feet per second, right? And so basically, initially when you let go of the rock, like that very split second, that the very instant you let go of the rock, it is not moving at all, let's say. But after 1 second, what's the velocity of the rock? Press pause on the video and write it down. What is the velocity of the rock after 1 second? It tells you there in the question. So the velocity is 32 feet per second. That's the speed of the rock, 32 feet per second. After 2 seconds, what's the velocity of the rock? Press pause on the video and write it down. Have you got it? It tells us here that the velocity increases by 32 feet per second for each second the rock falls. So if it's falling for 2 seconds, the velocity becomes 64 feet per second. Now again, there is such a thing as air resistance that is slowing this down a bit. So it's not going to just keep getting faster and faster forever until it goes a million feet per second. But we're just going to discount air pressure for now because we're just talking about the initial, dropping it from a building or something. The air resistance is minimal, all right? Anyway, so after 3 seconds, what would the velocity be? What would the speed of the rock be after 3 seconds? After 3 seconds, the speed has increased again by 32 feet per second. So it'll be at 96 feet per second is the new speed. So after 1 second, the rock is going 32 feet per second. After 2 seconds, it's going even faster, 64 feet per second. After 3 seconds, it's going even faster, 96 feet per second, right? So, So the question is the velocity of the rock a linear function of the time since it was dropped? And this table really helps me answer that question. So the velocity of the rock for every second, it's increasing by 32 feet per second each time. See, up 32, up 32. As the seconds increase by 1, as the seconds increase uniformly, the velocity is increasing by a constant. So we can see velocity increases at a constant rate. 32 feet per second. Therefore, we have a linear function. Okay? And if you graph this, which you don't have to, but if you graph this, it would look like this. Okay, I'll just do it really quickly. Time 0, 1, 2, 3. This is time. And then velocity. 32, 6, this is scaled, 32, 64, 96. Okay, and what would our points look like? 0, 0, 1, 32, 2, 64, 3, 96. You would find that that's a straight line graph, linear function. See that? So yes, it is a linear function, straight line graph increases at a constant rate. Okay, so that's the answer to that question. All right. So the next question is so now we want to take a look at the distance the rock travels, which distance is a totally different thing to velocity, right? Let's look at distance. And distance is just measured in feet. That's it. And we're told that physics tells us the distance in feet it falls is given by 16t squared. 16t squared, whereas t is 16t squared, whereas t is time, right? So let's look at that. I'm just going to plot it on the table. Same thing. So I'm going to say after 0 seconds, when the instant that you let it go, the distance is just 16 times 0 squared, which is 16 times 0, which is 0. It hasn't gone anything. That very instant you let go of the rock from the top of the building, it hasn't gone anywhere, so the distance is 0. After 1 second, how far has it traveled? The answer is you go 16 times 1 squared. Calculate that. Press pause on the video and calculate that. 16 times 1, 16. It has gone 16 feet after 1 second. Alright? But the problem is, well, hold on a second. So in other words, after 1 second, the rock has gone, let's say, from there to there. Okay? That's a distance of 16 feet from when it was dropped at the top of the building to as far as it traveled after 1 second. You with me? Now, you may ask, well, what's this 32 business that we calculated earlier? That is the speed that the rock is traveling at the end of 1 second. At the end of 1 second, the rock is traveling at a speed of 32 feet per second. But it has gone a total distance of 16 feet from when you dropped it after 1 second. Why? Because it's not 32 feet per second the whole time. It starts out at 0 and it increases its speed until it reaches a speed of 32 feet per second after 1 second. But over that period, as it has increased, it has been accelerating as it's been dropped down the building, right? Accelerating. And during that 1 second period, it went a distance of 16 feet. Does that make sense? Let me do the second. It might help explain as well. So after 2 seconds, we have the distance is 16 times 2 squared, which is 16 times 4, by the way, because you just square the t. It's a t squared, not 16. So 16 times 4, press pause everyone, calculate that. And you should get 64 feet. Which is not the same thing as over here. That over here is 64 feet per second. That's a speed. 32 feet per second. 96 feet per second. A totally different thing than the numbers we have over here, which are feet. This is distance. This is just like distance, right? So what's happening? In the next second, it traveled a total distance of 64 feet. By the way, that's from the top to the bottom. So it's kind of like, let's see, 64. Yeah, gosh. I'm going to have to adjust my my picture here. 1 sec. So what's happening? If the second, like this is the building, right? So it went 64 feet. That's 64, by the way, from like the top, like, or from where the rock was dropped. Let's say here, right? The rock was dropped from here, and it went, now this is not to scale, but I'm just a sketch here. The rock went 64 feet from here to here. That's the total distance it went. It just so happens that the speed of the rock after this is in a 2 second period, 2 seconds, 2 second period. After 2 seconds, the speed happens to also be 64 feet per second. Feet per second. Feet per second. But that's not the same thing as the distance it went was 64 feet. Okay? So you might find that a little confusing, but they are two different things, right? That's a speed, this is a distance. Okay. Now let's try the next second just for fun. So after 3 seconds we have 16 times 3 squared, which is 16 times 9, which is almost 160. But it's less than 160. It's 144, right? And that's 144 feet. So I'm just going to pretend, just for the fun of it, that after 3 seconds, that's when it hit the ground. Let's see. So after 3 seconds, the rock, you can show it all there. Yeah. Not exactly. Well, okay, show it all there. After 3 seconds, the rock went from the top of the building, or just above top building, all the way down, just for fun, to the bottom, right? So this is after 3 seconds. And it went from the top to the bottom. It went a total of 144 feet, right? That's the distance that it fell, 144 feet. But when it got to the bottom, its speed had increased to what? What was the speed of the rock after 3 seconds? The velocity, rather, sorry. And over here you can see 96 feet per second. So that was the speed it was at after 3 seconds. And we'll just imagine it hit the ground just for fun. But the distance it went was 144 feet. All right. So again, distance, speed. Velocity is speed, right? Does that make sense?
Yeah.
So distance, speed. Yep. So to answer the question is the distance a rock falls a linear function of the time since it was dropped? Is the distance it falls a linear function of the time since it was dropped? Let's see. The distance from our time, we made this up where we're like, our time is going from, seconds, 0, 1, 2, 3, and our distance is going 16 feet, 64, 164. So from 0 to 16, it's gone up by 16. From 16 to 64, it's gone up by 48. Right? Already we can tell it's not linear because these increases are not the same, right? From 64 to 144, it's gone up by, I think that's 80, isn't it? Yeah, so 80. And so no, our increases are not the same. So basically, the question is the distance a linear function of time? So we say the answer is no. Distance is not a linear function of time. Rock was since rock was dropped, okay? Distance is not a linear function, but velocity is a linear function. Velocity is linear, distance is not. That make sense?
Yes.
Now, if we really wanted to, we could do a quick graph. Sheesh, time, distance, and it would look something like this. Time, 0 seconds, 1 second, 2 seconds, 3 seconds. And the distance would be, let's see, 0, 0, that was 1. And then something like 116, which is about, we'll just call it there, I'll just make it up. 264, ooh, 64, that's a bit up. That's like something like here. All right, 264, something like there. And then 344, that's another jump. So like 144 be around there. So that's up there. So if you've graphed your distance, it would look like this. It would be a curve. And by the way, that's a quadratic function that you've seen before. Distance equals 16t squared. Notice that when you've got a squared in the input, you end up with this parabola. Remember the quadratic? That's a quadratic function. Okay? Curve up. This is a linear function. Straight line. Linear, straight line. Quadratic, curving. Got it? So there we go.